1. All right, so we are on 5.7. Submit your notes for 5.6 if you haven't already. If you've done the worksheet for 5.6 and you want credit, email it to me as a PDF, right? Okay, so what we're doing in 5.7 is important for advanced studies in mathematics. So that's why we're getting to this. Everyone knows tangent, right? That's the one parent function you still need to know. But now we're going to do inverse trig function. So let's look at the function f of x equals sine of x, right? It's the sine function. It's a function of x where x is your input, right? And it's an angle, typically in radians. And then the output is the sine of the angle, the ratio itself, right? So every function has an input and an output, right? Like a wood chipper. So the input is the angle, the output is the ratio. Well, we're going to look at the inverse trig functions in this section. And in general, what does an inverse do to any function in general? It inverses it, right? So if I multiply by 5 and I want to get my original number back, I would apply the inverse function to multiplication to get it back, right? Which would be what? Inverse multiplication, which is called division. Very good. So inverse operations, remember, undo each other. They undo each other. Back in the day, we found inverse equations by switching x and y. So that's what we're going to do, okay? In this section, we're going to flip it around. So our input is not the angle. Our input is going to be the ratio. And our output is not going to be the ratio. Our output is going to be the angle, okay? Whoa, right. So let's go ahead and practice. We are going to need, it looks like, we'll need a calculator. So if you want to get up and grab your calculator, dude. Oh, that's awesome. Yeah, that's awesome. Calculator. I like that. That's better. I'm going to use that if you don't mind.
Wait, calculator? Isn't that for like an amazing work on all episode? No.
It's amazing. I'll say that. Calculator. That makes it almost sound like a superhero, right?
It is a superhero.
Calculator.
It's the math equivalent of Skeletor.
Yeah, that's what I'm thinking. I'm thinking He-Man, right? Yeah, I'm thinking He-Man. All right, so here we go. Example 1. If sine of theta equals 5/7, solve for theta between 0 degrees and 360 degrees, right? So when I solve for theta, theta is the angle, theta is the input, and the output is the sine of theta, which is also 5/7. So whenever we're solving a conditional equation like this, we need to algebraically manipulate the expression so that we get it down to x equals something, or in this case, theta equals something, right? And that's what you learn algebra. But in this case, we have sine sitting in front of theta. How do we undo taking the sine of something? We did this earlier in chapter 5. How do we undo taking the sine of something?
Negative sign?
No, the inverse sine. So I'm going to take the inverse sine, which we write like that, of both sides. Okay? It's an operation, so it goes in the front. So I'm going to have the inverse sine of the left side, which is sine of theta, and the inverse sine of the right side, which is 5/7, right? So what we do to one side of the equation, we have to do to the other to keep it in balance, right? Now, what happens on the left side? What is the inverse sine of sine of theta? It's theta, right? Because those are inverses of each other, they undo each other. When you compose two inverse functions back to back, they undo each other, right? 3 steps forward, 3 steps back, right where I started, right? Yeah. So theta equals inverse sine of 5/7. Okay, so this is the inverse sine. Now, this is the inverse sine operation. Inverse sine operation. It's not the inverse sine function. The way we read this and the way we've done it in the past is this. I want to find an angle whose sine is 5/7. Well, let's think about what the graph of sine looks like. Let's quickly sketch Sahala. Several cycles, nothing too fancy. There's Sahala, right? It goes up to 1. Where's 5/7?
Below 1.
Below 1, but above 0, right?
Yes.
Let's call that 5/7. How many angles then are associated with the sine value of 5/7. Infinitely many, right? There's always two within one rotation, plus all the ones that are full rotations away, which we call what with it? Coterminal. There's infinitely many solutions. So, first of all, if I'm doing the inverse sine operation, I can't list all of them, right? I can maybe find all of them and then say plus multiples of 360. But if we look up here, yeah, this helps. This narrows down the search. We're only going to look between 0 degrees and 360 degrees, which is one positive rotation, right? So let's think about it. How many solutions will I have then?
One, two. No, two.
Two. Good. Because if we look at the unit circle, instead of the graph here, it's going to be positive in quadrant 1, and it's going to be positive in quadrant 2. So if you look at it on the graph, I'm looking for, like, here's one cycle of sine right here. We're looking in this interval. I'm looking for this one and this one, right? Or if you're looking on the unit circle, I'm looking for that one and that one. So there's two solutions, okay? So let's find them. We go to the calculator, and we have to go to mode first, right? Check yourself before you wreck yourself. Wow! It is already in radians. We want to make sure it's in what? Degrees. Very good. The calculator must be in degrees. Okay. Boom. Why degrees, Brady? Right. You see the degrubble. Now we go to our home screen and we hit second sine, right? Second sine, and you see it says sine inverse of 5/7. We've done this year. Boom. Your calculator is always going to give you one answer. It gives you 45 degrees. Well, that's the one in quadrant 1, 45.5. Yeah, wait, I'm waiting.
Or what? Wait. This isn't a calculator, it's a calculator.
Or calculator. Okay, I'm sorry. Yeah, my bad. Thank you, Brady. So the calculator gives us one solution. No, thank you. I need to be saying it that way. So let's go ahead and write it down. I'm going to say theta 1 is 45.584 or 585 degrees. Now, how do I find the other one? The calculator, if I just retype it in, is not going to give me a different answer. It's going to give me the same thing every time. Whose job is it to find the other one? Yeah, it's ours. So remember, this angle here is 45.584, as is this angle, right? So it's not only the angle theta, but it is also the, what do we call it? Reference angle. And so now I know how to use the reference angle. I need to get to theta 2 by stopping 45.584 short of 180, right? So for the second one, and I don't need to show that on my paper anymore, I'll put theta sub 2 is 180 minus, do I type in 45.584? No, I hit second negative, the answer. Okay, unless you stored it. And that's 134.415 degrees, okay? Now, if it didn't specify between 0 and 360, if it just said to find all of them, physically impossible to list them all. But here's what you could do. You could just say plus 360n, where n is an integer. And here you could say plus 360n, where n is an integer, right? What would that do? That would leave it to the person who's interested to generate any other solution in the whole wide world that he wants by either adding or subtracting multiples of 360 to find the other ones that are what with these two again? Coterminal, right? So anyway, warming up your desk, Rayleigh. Yeah. So anyway, it didn't ask us for that. So here's just our answer right here, these two guys. All right, so that's the inverse sine operation. It's the operation because we performed that operation on both sides to solve for theta, and here we had two solutions. Now, if we're talking about inverse sine the function, what's wrong with this? What's wrong with having two solutions if we want to have inverse sine, bless you, the function? I put in a log to a wood chipper. One time I'm going to get out wood chips, and then the next time I'm going to get out potato chips. Is that how it works? No. Yeah, functions must have at most one output, right? At most. They don't have to have an output, right? You put a bar or metal bar into the wood chipper, it breaks it, right? It's not in the domain. But if it does have an output, it's only one. It's predictable. So here we have two outputs. So if I didn't specify that, I would have more than two outputs. I would have infinitely many outputs. Oh no. So how can we talk about inverse sine the function if it has infinitely many outputs and we're supposed to have just one? How do we get rid of all the others? Boom. What'd you say? Louder. Say it into the earpiece right here.
Restrict the domain.
Oh, that's beautiful. Did you read ahead or did you just wake up knowing that? Oh man, he woke up like that. That's good. Must be nice. We are going to restrict the domain. We're going to restrict the domain. Okay. We are going to agree upon the values of X for the graph of sine that we're going to use so that when we take the inverse sine of something, we always get one answer and it's in that restricted domain. And guess how your calculators are programmed? If you go to mode, right below radian and degree, you see funky mode, right? Your calculator is by default in funky mode, right? Your calculator, sorry. That's function. Your calculator is in function mode. It knows to give you one answer and one answer only. And that's why it does. So we're going to look to see at what interval are we going to restrict the domain to and why? That's always a good question. Why are we going to restrict it to that one? Okay. Good. All right. So let's look it down here. When we talk about inverse sine the function, we're going to call it f of x again. We like to use x as our independent variable. So f of x equals inverse sine of x. X is still our input, but now because it follows an inverse sine, not a sine, the input x represents a what? The ratio, and the output is the angle. Okay, we flipped them. Okay, so when you see inverse sine of something, the thing that follows it is always a ratio, a unitless ratio, and your job is to find the one angle whose sine is that ratio. Okay. All right, so let's review one-to-one function. We talked about it yesterday. One-to-one function is basically like Minnie and Mickey. For every Minnie, there's only one Mickey, and for every Mickey, there's only one Minnie. And I just learned that the voices of Minnie and Mickey for years and years and years and years were a husband and wife team. Believe it or not, that's true fact. So yeah, for every Mickey's voice, there's only one Minnie's voice and vice versa. It's cute how that worked out. It has to pass the horizontal line test. If a function is one-to-one, we say it's invertible. What does invertible mean? We talked about that earlier in the year. That means it has an inverse that is also a function, right? There's only one way to code the message, and there's only one way to decode the message. That's a one-to-one, okay? We want to make sine and cosine and all the trig functions, we want to make them one-to-one so that when we find the inverse, there is only one way to decode it, right? So we want to restrict the domain to a one-to-one interval that passes the horizontal line test. That way, there's only one output for every input and vice versa, okay? So let's go ahead and look at sine, and we'll talk about why we're going to restrict it, okay? Let's draw sine now just a little bit more detailed than what we did above. We did this yesterday as a warm-up as well, right? You should be able to quickly sketch Sahala. So it goes up to 1, it goes down to -1. Here's 2 pi, here's pi, here's pi halves, there's 3 pi halves, right? And then we do it over here. There's -2 pi, -pi, -pi halves, and then -3 pi halves, right? So if you see how I do that, I always go out to the period, bisect, and that kind of works nicely for me. You can have your own method, but we've set the table. Now for Sahala, we start on an axis. Axis high, axis low, axis, right? And then working backwards, it's low axis, high axis. And then we connect it with these beautiful curves. Man, how many times have we sketched sine? Not enough, not enough. It's artwork, right? Yeah. I have one of my early drawings of sine hanging above my sofa in my house. It's beautiful. It's an early work. So it's kind of raw and unrefined, you know. Is sine of X 1-to-1? Is this graph 1-to-1?
Yeah.
It's a function because it
Right,
passes the
yes.
vertical line test. But to be a 1-to-1 function, it has to pass the horizontal line test. Does it pass the horizontal line test? No, we just said that. For 5/7, there were infinitely many values associated with it. So here's the deal. This is what we want to do, okay? We want to restrict the domain of sine of X to, here are the criteria, is number one, convenient, if I can spell that right. Is that how you spell convenient for, why am I having a hard time? To a, what's another word for convenient?
Easy. Good.
Yeah, I'm gonna put convenient. Is that right? That looks weird.
Radical.
Okay, to a convenient, yeah. For some reason, it's just looking weird. 1-to-1 interval. Okay. That, number 3, includes all the sine ratios from -1, from y equals -1 to y equals 1. There are lots of 1-to-1 ratios we can pick, or intervals we can pick, but if it doesn't include all of the sine ratios, it's going to be incomplete, right? Like if for some reason I don't include the 1/2 ratio in my interval, and I ask you inverse sine of 1/2, you'd be like, well, normally that would be pi6 and 5 pi6, but 1/2 is not in my interval, so there's no solution. That's not good, right? So I want a convenient 1-to-1 interval that passes the horizontal line test that includes all of the sine values from -1 to 1. Does anyone have a prospective interval? We're looking for values of X from something to something.
Are we looking in full or halves?
Okay, so how about from 0 to pi halves? Is that convenient? It's convenient because why? What's our criteria for that? It's near the origin, right? It's one of the first things we graph when we graph. It's near the origin. Is it 1-to-1? Is that little yellow piece 1-to-1? Does that little yellow piece pass the horizontal line test? Yes. But does it include all the ratios from that? No, it doesn't. It only includes the positive ones. So what if I go down this way?
No.
That's convenient. It's still near the origin, but is it 1-to-1? Okay, so let me back it up here. What if I look at this, Brady? What if I look at this interval? Is that convenient? It's not too inconvenient. It's still near the origin. Is it 1-to-1? Yes. Does it include all of the ratios from -1 to 1? It does. So is that the one we want to choose, or is there a more convenient interval? Ah, excellent. Excellent. Negative pi halves to pi halves. That is another convenient interval, but this one's actually a little more convenient because it's closer to the origin. It straddles it on either side, which is okay, but it's a little bit closer than -3 pi halves to pi halves. So it's the closest, most convenient interval. Is it 1-to-1? Yeah, it's 1-to-1. And does it include all the ratios from -1 to 1? Yes. So this is the agreed upon interval. We are going to restrict the domain of sine from negative pi halves to positive pi halves. Okay. And if we then reflect that across the magical line for all reflections, the line y equals x. Okay, what happens if you reflect it across the line y equals x? What does it look like? Can you imagine it?
Kind of looks like you can pull it in on itself.
Kind of. Well, here I'm gonna go old school low key for you here. Just yeah, let me draw something here. Drawing something. Yeah, turn your head, get crunk. Dun, 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 dun. Good morning. Okay. This is how people learn before iPad. And if you're on the video, you're like, I can't see. I can't see. What you doing? What you doing? Mama, I can't see. Your computer's broken. Well, maybe a squirrel got into it. No, I think one of the ones got stuck in the cable. The zeros can go through nice and easy like because they're rounded, but sometimes the ones get stuck. Why don't you shake the cord? That's improv. Okay, so does everyone see the graph of sine of x in blue?
Maybe.
Okay, I can't see it. Well, you need to be here live. Does everyone see the green part that I highlighted? That's our agreed upon 1-to-1 interval. Okay, the red line is the magical line 1 over x. Here's how you can visualize what it looks like. I'm going to hold my fingers at the edge of the paper here, okay, on the diagonal. And all you have to do to reflect it across that line y equals x is just flip the paper. See, I didn't move my hands at all. First of all, what happened to the width of the paper? Landscape became portrait, right? So the x-axis becomes the y-axis, and the y-axis becomes the x-axis, right? The x values become the y values, and the y values become the x values. So again, it's easy to visualize, right? If you can see it reflected across the line and you see what the green looks like on the back side of the paper, that's what the graph of inverse sine looks like, okay? Y'all see it? So I'm gonna look at it from your perspective. It's an increasing function, kind of like x cubed, but it stops, right? It literally stops. It doesn't keep going, right? So it's actually more like John Travolta, the disco graph. If you put, instead of fingers at the end, if you put like knuckles, right? Now it looks like, right, here's inverse sine, right? Dance fever, dance. Yeah, so there you go. There you go. There's a low key model, low key model. Nice, thank you. All right. So, thank you very much. Let's go ahead and sketch what the graph of inverse sine looks like, okay? It's going to be like dance fever. So I'm going to put a little knuckle right there. And it's going to come up here like that. And then it's going to come over here like that and another knuckle. All right. Now we're going to label the y-axis, not negative 1-to-1, because the y-axis is now the x-axis. That's negative 1-to-1. The old x-axis that we restricted from negative pi halves to pi halves, that's your new y values, okay? This is the graph of inverse sine of x, also known, I'll throw this at you right now, also known as arc sine of x, okay? They mean the exact same thing. We sometimes, I prefer arc sine because the inverse sine kind of looks sometimes like a reciprocal. It can get confused for a reciprocal. But when we say arc sine, that's the same as inverse sine, and there's no mistaking it, right? And so why do we use the word arc? Well, it's related to the arc length of a radius, of a radian, okay? So that's where it comes from. So they're the same. What's the domain of arc sine or inverse sine? Negative 1-to-1, right? Those are the allowable ratios for sine. And what's the range of inverse sine? Good. negative pi halves bracket to pi halves bracket. Okay. Now we call this the PVR. You could just call it the range if you want, but I typically call it the PVR. What does PV stand for? Principal value range. Okay. Principal means not only my pal at school, right? Your principal is your pal at school. That's how you remember how to spell it. But it also means what? Like this is the principal branch of our bank. The best, the main, right? It's the main, the primary. Good. So this is the primary range. There are other ranges, right? Somebody in some weird culture, or weird cult might decide to restrict the domain from -3 pi halves to negative pi halves. That's fine. There are other intervals, further down the line. You could go from here to here. You could keep going down the line and say, well, in our society, we use this. Okay, that's fine. That's another range that you are entitled to use. But this one is the one that most people agree upon as the most convenient. So that's why we call it the principal value range or just the range, okay? I like to say PVR because it's shorter than principal value range, but it also implies that there are other ranges out there. We had to restrict the domain to make it work. This is what your calculators are programmed in, okay? So anytime you take the inverse sine of a positive ratio, you're going to get out a positive acute angle. And anytime you take the inverse sine of a negative ratio, you're going to get a negative acute angle. Yeah. So that's why it was always in quadrant 1. If you want to think about it on the unit circle, the PVR for arc sine is this. Okay. I call this the half moon. It's quadrant 1 and quadrant 4. But if it's in quadrant 4, you don't get there by going all the way around. No siree. You get there by going straight down to it clockwise in a negative fashion. So if you're wondering why your calculator, when you did inverse sine, never gave you an obtuse answer, it's because of the PVR. It's programmed in the PVR. It'll always give you an acute angle. If it's a positive ratio, it's a positive acute angle. If it's a negative ratio, it's a negative acute angle. Now you know. You do need to kind of know the PVR for inverse sine moving forward. Okay, it's half moon, half moon. All right, half moon. All right, let's try this out and we'll be done, right? If f of x is inverse sine of x, evaluate the following from the unit circle. I guess we don't need our calculator for this. So f of 1/2, well, that's inverse sine of 1/2, or that's arc sine of 1/2, either one. So the way that you need to read this is sine of what angle in the principal value range gives us 1/2. Well, normally you would say sine is positive in quadrants 1 and 2. And what would the angle be? It would be pi 6 or 5 pi 6 within one rotation. But is 5 pi 6 in the PVR? It's over here. So the only answer is pi 6. If you take the inverse sine of 1/2 on your calculator right now, it should give you pi 6 in degrees. What is pi 6 in degrees? 30. Go for it. Hit second sine of 0.5, enter, and it'll give you 30 degrees if you're in degree mode all day long. I'm not going to verify it, but you can do it, right? Right? You got 30 degrees. Yeah, absolutely. Never not 30 degrees. Okay. Let's do part B. What would f of -1/2 be? Well, what's inverse sine of -1/2? Well, that's the same as arc sine of -1/2. What is it, Brady? Oh, well, it's going to be in the PVR. Let's get rid of this disgusting picture. What's the PVR for sine? It's half moon, so it's 1 and 4. Sine is negative in only one of those two quadrants, right? Which is quadrant 4. Now to get there, I'm not going all the way around. No. I'm getting there by going straight down, which is not 11 pi 6, but negative pi 6. So if you type in second sine of -0.5 on your calculator and you're still in degree mode, calculator, you're going to get -30. Try it. Second sine of -0.5, enter, -30. I just thought of a new meme. Okay. Drake backing away. Well, here's at the top, inverse sine of -1/2. That's at the top of the meme. Drake backing away would be 11 pi 6. Drake smiling, negative pi 6. Is that a good meme?
Yeah.
Yeah. Did I use the meme correctly? You know what I'm talking about? Okay. I'll make that happen. I'll put it up there too, so that when you're taking a test, you're like, oh, I don't listen to Corpy, but I will listen to Drake, because all Canadians are nice and friendly and speak the truth. See? That's a good meme. That's a good meme. I like that meme. It's kind of the yeah. Okay, there you go. There you go. All right. There you go. Let's finish these out. What is f of negative square root of 3/2? Well, that's arc sine of negative square root of 3/2. What's the PVR for arc sine? Half moon, right? 1 and 4. Sine is only negative in one of those, right? So it's got to be in quadrant 4, not in quadrant 3. It's got to be in quadrant 4. And to get there, we go straight to it. So we know it's a negative angle, right? And what's the reference angle? Negative pi thirds. Good. It's the answer. If you type in inverse sine of negative square root of 3/2 in degree mode, you're going to get negative 60. Here's what's easy for arc sine. A negative ratio, a negative angle. A positive ratio, a positive angle. And they're always acute, right? Coochie, coochie, coo. They're always acute. Always cute. Positive ratio, positive acute angle. Negative ratio, negative acute angle, right? Okay, let's do this one. Letter D, f of 1. That's inverse sine of 1. Oh, sine of what angle is 1? Well, the PVR is here and here, but that's not an interior ratio, right? That's one of your quadrantal angles. So what is the answer? Is it pi halves or negative pi halves, which is coterminal 3 pi halves? It's pi halves. Yeah, on your calculator right now. Type in second sine of 1, enter, and you should get 90 degrees. Ooh, summer's coming. 90 degrees, yeah. 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 Hey, if you're cold in here, you could either put on a Snuggie that's in the hall, in the corner, in the cabinet over there, or go stand in the corner, because it's always 90 degrees. In fact, the construction building this place was so bad. If you stand in the corner, it's probably like 94 degrees, because you know, we used the lowest bid to build the school. So nothing is perfectly square, right? Yeah, so you overheat a little bit maybe. All right. What about this one real quickly? What is f of -1? Tell me. Negative pi halves. Good. Negative pi halves. If you type it into your calculator, inverse sine of -1, enter, you're going to get negative 90. Negative 90. It's cold. Winter's coming, right? Game of Thrones. Yeah. Okay. All right. And then the last one here, f of pi. That's inverse sine of pi. Ah, I got you. Got him. Oh, yeah. What's sine of pi? 0. But what's inverse sine of pi? DNE. Ah, I did that on purpose. You're an audience plant. You did that because I asked you to. Thank you. Thank you. Yeah. We got to know the difference, right? Pi as an angle, the sine of pi is 0 the ratio, but inverse sine of pi doesn't work because pi is outside of -1 and 1, right? You can't have a sine ratio that's 3 times, where the short side is 3.14 times bigger than the hypotenuse, right? That doesn't work. So that's why it's important to know the difference. Okay, pi in this case is just a number. It's an illegal ratio. It's not between -1 and 1, so it's DNE. All right, good. So go ahead and clear your calculators, put them away. We're going to stop right there on example 3. I don't know if we're caught up with Mrs. Lincoln, but who cares? Forget about it. Forget about it. Like an even fun. Yeah, we do. Okay, awesome. Y'all have a good rest of the day. It's a pep rally schedule. So I'll see y'all at the Powder Puff football game. It's on the wall over there, Brady. Over there.